Thank you. Hi, everyone. Thanks, Alexander, for the introduction. All right, very excited to talk about this modern era of statistics. So you've heard throughout the lectures probably a lot about the deep learning and the technologies that enables this. But what I want to talk about, I want to say why it works, okay? So, and give you some intuitions about where we are standing in terms of the theoretical analysis of this system. Because a lot of people think that machine learning is an ad hoc field, and deep learning is extremely ad hoc. Just change a couple of hyperparameters and everything starts working. But that's not actually the case. So we have some cues like what's the whole thing is about, okay? All right, so to motivate, I want to tell you about this, I think it's a very common photo these days, that you can see that the Moore's doubling law got broken after 2012, and we got into kind of a new type of models that as we growed in size, on the y-axis here, what you see is the energy consumption of these models. It could be even accuracy, the accuracy of these models or generalization ability of these models goes higher and higher as we scale them, okay? And that's the kind of observation that we had so far. And that's what I mean by modern era, because we are exhaustively increasing their size. As this photo can show you like some scale of these large language models that are out there. You can see that we have models up to 540 billion parameters, where it's beyond our understanding how these models perform representation learning. And it's not only in the realm of language modeling, but it's also across like different fields. For example, in time series modeling, in medical diagnosis, in financial time series, we have new technologies that are getting better and better with size. And this seems to be the case across different data modalities. And perhaps the one that Ava was presenting before, generative modeling, we went from, in 2014, generative models like that to generative models like this, right? So the quality drastically improved, not only because of the size, but also the underlying structures that enabled us to scale these neural networks. Because we already knew that if you have stack two layers of neural networks next to each other, you have a universal approximator, right? So then why couldn't we scale it? Now we had to find the right structure in order to do that. For example, diffusion was one of those structures that Ava actually presented. So it seems like bigger seems better, but why? Okay, let's find out the reason. So you all, I assume that you would all know how to solve these two equations. So n equations requires n unknown, right? So how many of you know still how to solve this kind of thing? Yeah, so I think it's pretty. But then the crazy thing about deep learning is that it comes and says that, yeah, make the number of these x and y larger and larger excessively for these two equations, and things would start working even better. And what does it mean even better when you have like two equations and you have like a lot of unknowns? How does that even make sense? Let's do an analysis, a numerical analysis of the Amini data set. You've all seen this data set before. It's a handwritten digit. And as you see, like it has 60K points. It has dimensionality of 28 by 28, grayscale images. And then today's models, they have millions of parameters to model 60K images. So the performance on this data set actually keeps improving as we scale the neural networks. And how does this make sense? Like, where is the information, basically, that we're learning from 60K images with millions of data parameters? What are we learning? Now, we know that generalization error or test error has this kind of proportion from the theory, that it's proportional to the number of parameters of the system over the square root of number of parameters of the system over the data set size. That means if I increase the number of parameters of my system, then I would expect at some point that generalization or the error goes high. So then why is it that we make them larger and larger, but they work? In case of ImageNet, another larger scale data set, very common in machine learning, we have like 1.4 million images of size 256, 256 tree, And then you have models with hundreds of millions of parameters that you feed these 1.4 million images. In NLP, as we showed before, we have data points of few billions and then models with 100 billions. And then perhaps like the best, and my favorite kind of illustration of this size improving performance in this generative AI, when you have a prompt, this is like a generative AI that receives text as input and generates output images. So the prompt or the input to this system was a portrait photo of a kangaroo wearing an orange hoodie and blue sunglasses, standing on the grass in front of the Sydney Opera House, holding a sign on the chest that says, "Welcome, friends," right? And as we see that on the top of each image, we have the size of the model. And as we improve the quality of the size of the models, the quality improves, and we're getting closer and closer to that description that we provided as an input to the system, right? Like the first image actually with 350, it still like has all the components of that input, but it's not as good as the last one, right? It misses on a couple of things. All right, so this happens, and let's now figure out a way to explain this, okay? How many of you have heard about a phenomenon called double descent? 1, 2, okay, good. All right, so, this is not a learning curve, okay, first. X-axis shows the model size. You have an image classification problem, CFAR 10, and these are 10 classes you want to classify these images. And now on the x-axis, you are increasing the size of the networks. And on the y-axis, we see the test error, okay? Let's just concentrate on the purple side of the process, because that's at the end of the training process, okay? We're looking at the test error at the end of the process. So classical statistics was telling us that as you increase the size of neural networks, up to a certain point, you find a nominal point where the performance of model, the generalization that you have is optimal. And from that moment on, if you increase the size of the network, you're overfitting. What that means like the kind of accuracy, basically that the first bell shape that starts going up, as you see, that part was going, and they projected that thing is going to go up as we actually scale the models. But then the phenomena that we observed is that there is a second descent as we scale the size. So this is called a double descent phenomenon. So the first descent we knew already. In the modern era, we figured out that as we scale these neural networks, the size of the models, and this has been observed across many different architectures, okay? So as we scale, it could be a ResNet architecture, it could be a convolutional neural network, it could be an LSTM or multi-layer perceptron or whatever that you know. But as we increase the size, that's the kind of phenomena that we see. Now let me make it a little bit easier to understand. This was classical statistics in terms of accuracy now. In the previous one, we were seeing errors. Now we see accuracy. We go high up to a certain point, and then as we increase the size of the models, we start overfitting. Now, up to a certain point. Now, if you have the new kind of experimental results showed that that's actually the case, where up to a certain point, we go up, and then again, there's an improvement in performance. This regime is called an overparameterization regime. I'll tell you more, and I'll give you more substance why we call them overparameterization regime. I mean, it should be pretty obvious, but I'll put it in the theoretical and the technical kind of language of machine learning. All right, so one of the things that we can observe from this image is that the accuracy at the very end of this overparameterization regime, you see that it's slightly better than the first accuracy that you get from a model that is reasonably sized, okay? It's not that much better, the accuracy. But then the discovery of deep learning was that when we're in the overparameterization regime, we get a new type of behavior starts emerging. What kind of behavior? The characteristics that emerge in that overparameterization regime is something that I'm going to talk about next. So one of the things is, as we go larger and larger in network sizes, they learn concepts that they can pass on to different tasks. That means they can generalize across different tasks. That means those concepts that they learn, they can be transferred to actually perform more tasks, not even a single task that they have been trained on, okay? So it seems like you're giving them more ability to generalize and getting closer to those kind of, a kind of general representation of AI. I'm afraid to say AGI yet, okay, but yeah. But that's the kind of thing that we observe. The kind of concepts that they learn, they are being able to perform across different tasks, across different domains. They get better and better. Another observation that we had is that the scale improves robustness. What does it mean for a deep learning model to be robust? That means if I change the input a little bit, if I perturb it with noise, on the output, it doesn't completely go crash. So the change at the input is proportional to the output changes. So robust means that you are being able to control the error on the output if you have a little bit of error or deviation at the input. So this curve actually shows that as we scale these neural networks, we see that the size of the robustness actually improves, okay? I'm gonna talk about this in much more detail because that's the part where we have the theory for, from a deep learning perspective. Now, not everything improves by growing in size. For example, the problems of bias and accountability and accuracy on minority samples, as we scale, they get worsened. So we have evidence for those kind of cases as well. So you need to be careful when you're deploying this in our society. Now, another very important part of intelligence, which is reasoning, the ability to logically talk about kind of different phenomena, is basically reasoning. And reasoning is basically stays unchanged. If you just scale a model, unless you provide the system with a simulation engine. Let's say you want to do physical reasoning. Let's say there are two cubes. They're both moving in on x-axis. One of them is faster than the other one. So one thing that you have as a human being in your head is a simulation engine that you can basically simulate that kind of reality. So if you provide that kind of reality to a language model, the results of that simulation to a language model, you would see, again, increasing reasoning. So that part is also extremely important. Now, the part that we are, like all these results that I'm showing here, they are very experimental. So there has been like large corporations involved to actually perform this kind of analysis to see the behavior of these large models. But do we have an actual theory that fundamentally is true about these models or this behavior that we see? Let me focus on the robustness, okay? This is from, this kind of graph is from Alexander Madry's group from here, MIT, where they're studying robustness in neural network. What they do, I mean, it doesn't matter what the three lines are. What they do, they try to attack the input images, and then compute the accuracy of models. As we scale, again, on the x-axis, we see the scale and accuracy. As we start increasing the capacity of the networks in image classification, Amini's classification here, we see that there's a jump in robustness. That means the attacks that they were doing or perturbing the input images with something called, an attack is called projected gradient descent. It was basically like you got into a really good accuracy after you actually increased the size of the network up to a certain point. And there was this transition, there was this shift in performance. And that has been confirmed, as I said, by experiments. And we said, all right, so scale, the conclusions of those kind of results was that scale improves robustness. But then, and the best paper award at the Conference on Neural Information Processing System, NeurIPS, 2021, came and said scale is a law of robustness. Okay, what that means? Okay, that means like let's formulate how scale is basically contributing to robustness. Okay, so I'm going to talk a little bit more technical about this thing. Hopefully you can all follow, but you can ask questions like even now if you have questions. Let me just finish this one, and then we'll take some questions. So let's say fix any reasonable function. What is a reasonable function? It's basically a function that has a smooth behavior, okay, like a sigmoid function, okay? That's a very reasonable function, okay? A crazy function would be like if you have like jumps across like different modes, you know, like you have a reasonable function, okay? And it's basically It's parameterized, okay, like a sigmoid function that you can parameterize it. And then it's poly-size, like it has also reasonable size in parameters. And it's not a Kolmogorov-Arnold type network. What does that mean? That means I'm showing you a representation that was discovered by Arnold and Kolmogorov that shows that there are this composition that we see can approximate any continuous function, multivariate continuous function. Okay, so these are basically two nonlinearities, and the sum operator is basically applying, joining the inner kind of processes. But one problem with these kind of functions is that they're non-smooth, and as Tommy Poggio actually mentions, they show wild behavior. Like they could be anything. The function, inner function could be anything. So let's rule out those kind of functions. Let's talk about only neural networks, okay? Like very reasonable functions and really function as well. Now let's sample n data points. For the case of MNIST data set, we have 60K data points. Truly high dimensional. I mean, MNIST is like 28 by 28 times 1, so it's like 728, right? So it's not that truly high dimensional. But let's say ImageNet is 256 times 256 times 3. So it's like truly high dimensional. And then add label noise. So why do we want to add noise to the labels? What does that mean even? That means we want to make the problem harder for the neural network. That means it should not be the mapping between the input, high dimensional input, and the output classes should not be trivial, okay? So we add noise, a little bit of label noise, to basically create this, a complex problem, okay? So that means like if you have all your labels are random, the problem is really complex, right? So you want to add a little bit of random noise as well. And then to memorize this data set, what does memorization mean? That means if I have a function and I'm fitting a parametric model like a neural network to it, I want to be completely fitting every single data point, okay, during training. That means I want to achieve a 0 loss on my training set, okay? That means like memorizing. So definition of memorization during learning. Now, optimize the training error below the noise level. And below the noise level, what does that mean again? That's like another definition that you guys have to know. Is, as I said, we want to complicate the process so that it's not a trivial mapping. So you add that noise, and then when your accuracy is a little bit higher than the amount of noise that you injected, for example, for the MNIST, basically the hard part of the training of the MNIST data set. Let's say if all kind of machine learning models can get up to 92%, 91% accuracy on the MNIST data set. But then what's the hard part? The hard part of it is the last 2% to 5% to reach the 100%. So that's the hard part. That's what we call below the noise level, okay? That means if you can learn this process really like with really good accuracy. Now, and to do this robustly, in the sense of Lipschitz. Who knows what is a Lipschitz function? Good. 5, 6, okay. All right, so Lipschitzness. So good that I put this in here. So as I said, look, so you're moving your inputs with epsilon, okay, a little bit of perturbation at the input of a function. Then if the output is also moving with epsilon, or proportional, linearly proportional to that epsilon, that means this function is Lipschitz. So you have a controlled kind of process. Change in the input do not dramatically change the output of a function. That's called the Lipschitz function. Now, yeah, so you memorize the data, and you want to do this memorization robustly. So if you want to do that, it is necessary, it is absolutely necessary to parameterize your neural network at least equal to n. N is basically the dimensionality of your data set, which is 60K, times D. D is the dimensionality of your of every input sample. Let's say if your input is an MNIST data set, I mean, I'm gonna give you an example later on, but let's say the input is 728 in the order of 10 to the power 3, and the number of data set is 60K, right? Then the minimum size of an MNIST data set has to be 10 to the power 8. That would be the size of a neural network model, 10 to the power 9, to robustly learn MNIST data set. That's a huge neural network. But this is one of the fundamental explanations, very recent, that we have about the theory of deep learning. And why is it called dramatic overparameterization? Because intuitively, as we showed before, memorizing n data points would require n parameters. And we had Eric Baum and David Hessler. They were showing that two-layer neural network with threshold activation function. They showed it in 1988, that you would need P is the number of parameters. You would need almost equivalent order of number of data points that you have. That would actually be enough, theoretically. And then they showed it recently for the ReLU networks. And we even have that in the neural tangent kernels. So how many of you are familiar with neural tangent kernels? Good. 3 out of 3. Good. Okay, 1, 2. Yeah, so neural tangent kernels is that. So imagine the process of training a neural network with gradient descent. The whole process from beginning of training to the end of training is a dynamical process. That means you're updating the weights of the system as you go further. Given a data set, given a neural network, and given the parameters of your optimizer, this learning dynamics can be converged can actually be modeled by a dynamical process, by a differential equation that explains how the updates of gradient descent of a neural network would work. Now, if I increase the size of the neural network to infinite width, if I increase the size of the neural network to infinite width, then this dynamic of learning has a closed form solution. That means it has actually a solution which is a kernel method. So basically, you will end up having a kernel, and that kernel explains the entire behavior and dynamics of your learning process in the infinite width. This is called the neural tangent kernel theory, and we have a PhD student who's actually sitting over there, Nual Lu, that is focusing on that, and this is actually his PhD topic that he's working on in Danielle's lab. Okay, so now let's move from this theory, and let's give an example. So we have the MNIST data set. It has around 10 to the power 5 number of parameters. The dimensionality of each data point is 10 to the power 3, is 728, so just the scale. And then we saw the transition in the kind of robustness. That means like at least you need to have 1 million, 10 to the power 6 parameters to robustly fit the MNIST data set. But then there are a couple of notes that we want to have. The notion of robustness in the theory paper was a little bit different than the notion of robustness and Lipschitzness that we showed in the theory of law of robustness. And then another point is that the law seems to be contradicted, because if you multiply, we just said the law is like, n times d, right? Like that's the minimum number of samples that you have the transition. So, but here, if you do that, 10 to the power 5 times 10 to the power 3 is 10 to the power 8, and it's much larger than that 10 to the power 6 that was observed in reality. But one of the things that you have to also notice is that there's something about data sets. It's called effective dimensionality. And effective dimensionality means that when I show you an image, there are principal components of an image. So finding the principal components of an image, that how small that image, what's the information? The information is not the same size as the pixel itself. The information is much smaller. So the effective dimensionality it's hard to actually determine what's the effective dimensionality of a given data set. But still, for the MNIST data set, it's 10 to the power 1, and now we have 10 to the power 5n. And if the effective dimensionality is basically at 10 to the power 1, then you would have basically the same, you can confirm with experiments the theoretical results that was observed with the law of robustness. Now, the noisy labels, as I said, it's basically learning the difficult part of the training. And then in regard to ImageNet, it basically shows the law of robustness predicts, because we haven't yet trained super large neural networks. It seems like the networks that we have trained so far, they're actually small. We have trained like really large neural networks still, but they have to be on the order of 10 to the power 12 or 10 to the power 10, And this is like the prediction of the law of robustness. Okay, so now let's get back to this image. So all these networks that I was talking about and law of robustness is basically in that regime. In that regime, I showed you that we have great generalization. We get more robust, provably more robustness. And then reasoning, still, we have questions about how to achieve it. And then bias and fairness, which is very important. Energy consumption and accountability of the models. There is a way, and that has been the focus of the research that we have been doing at Daniela Russo's lab with Alexander and a couple of other graduate students of ours, is to find out how can we get out of that overparameterization regime while addressing all these socio-technical challenges. And how we did that, we went back to source, okay? Basically, we looked into brains, okay? We looked into how we can get inspiration from brains to improve over architectural biases that we have in neural networks in order to break the law of robustness. Now, and then we invented something called liquid neural networks with the direct inspiration from how neurons and synapses interact with each other in the brain, okay? That's how we started our focus. In the second half of my talk, I'm just gonna talk about liquid neural networks and their implications in this realm of modern era of statistics. So, as I said, we started with nervous systems. Then, in order to understand nervous systems, you want to go down and you can look into neural circuits. So neural circuits are circuits that are composed of neurons. Then they can get sensory inputs and generate some sort of outputs, motor outputs. And then we went even deeper than that, and we looked into how neurons, individual neurons, communicate with each other, two cells receiving information between each other. And then we arrived at an equation that, or a formulation for the interaction of neurons and synapses that is abstract enough so that we can perform computation, efficient computation, but at the same time has more details of how the actual computation happens in brains, and not just the threshold or activation, very kind of the sigmoid function that we always see. So let's get in, more deeper into that. And we showed that if you really get into more biologically plausible representation of neural networks, you can gain more expressivity. You can handle memory in a much more natural way. You gain some properties such as causality, and which was basically something that we haven't discussed. And what's the cause and effect of a task? Can we actually learn that? You can get to robustness, and you don't need to be crazy, like large, be out of that regime. You can perform generative modeling, which was what I described before. And you can even do extrapolation. That means you can even go beyond the kind of data that you have been trained on. That means you can go out of distribution. So that's something that we couldn't do. And the area that we were focused on was robotics, real world, like we called it mixed horizon decision making. That means if you have a robot interacting in an environment, in a real setting, now how to bring these kind of networks inside real world. And that's the focus of our research. So what are the building blocks of this type of neural networks? I said the building blocks are basically interaction of two neurons or two cells with each other. Some observation about this process. The first observation is that the kind of interaction between two neurons in the brains is a continuous time process. So that's something to account for. So we're not talking about discrete processes. Another thing is that synaptic release. Right now in neural networks, when you connect two nodes with each other, you connect them with a scalar weight, right? Now, what if I tell you that when two neurons interact with each other, it's not only a scalar weight, but there is actually a probability distribution that how many kind of neurotransmitters generated from one cell is going to bind to the channels of the other cell and how it can actually activate the other cell. So the communication between the nodes is very sophisticated, and it's one of the fundamental building blocks of intelligence, which we have actually abstracted away in artificial neural network to a weight, to a scalar weight. Now, another point is that we have massive parallelization and massive recurrence and feedback and memory and sparsity kind of structures in brains, and that's something that is missing from not entirely, but somehow it's missing from the artificial neural network. So we deviated a little bit. Now, what I want to argue is that if we incorporate all these building blocks, we might get into better representation learning, more flexible models and robust, and at the same time be able to interpret those results. And this, because of the first reason that the whole process was built on top of continuous time processes, let's get into these continuous time processes and where we are in terms of neural networks with continuous time processes. So here, I'm showing you an equation. So F is a neural network. It could be a 5-layer neural network, 6-layer neural network, fully connected. But this F that has n layers and width k, and then it has certain activation function. It's a function, that means it receives input, it receives recurrent connections from the other cells. It receives exogenous input as well, like this I, and it is parameterized by theta. Now this neural network is parameterizing the derivatives of the hidden state, and not hidden state itself. That builds a continuous time neural network. Now, if you have a continuous time process, that means like the updates or the outputs of a neural network is actually generating the updates of your the derivative of the hidden state and not hidden state itself. What kind of, you can give rise to continuous time dynamics with neural networks that we haven't explored before. Now, what does this mean in terms of like neural networks? Let's look at this image. How many of you have heard about residual networks? Okay, residual networks are deep neural networks that have a kind of a skip connections, okay? Like from one layer to the other one, you have basically skip connections. And that skip connection is modeled by this equation ht plus 1 equal to ht plus f of whatever. That ht is basically resembling basically a skip connection. And now here on the y-axis, what we see the depths of neural network, and each dot, each black dot here shows a computation that happened in the system. So when you have a neural network that is layer-wise, like let's call it layer-wise because the photo is actually showing the layers in the vertical axis. So if you look at the vertical axis, you see that computation happened at each layer, okay? Because as the input is computed from the first layer to the second one, and then to the next one. But if you have a continuous process equivalent to this process, you have the ability to compute at an arbitrary point in a vector field. So if you know what are differential equations and how do they basically change the entire space into a vector field, how can you basically go, you can do adaptive computation, okay? And that's one of the massive benefits of continuous time processes. Now, in terms of things that you have seen before, standard recurrent neural networks, you had the lecture here, so a neural network F is basically computes the next step of the hidden state. So it's a discretized kind of process of updating the next step. A neural ODE updates the state with a neural network like that in a continuous time fashion. And then there is a better, more stable version of this differential equation that is called continuous time or CTRNNs, recurrent neural networks. There are continuous time recurrent neural networks where they have a damping factor. So that differential, it's a linear ODE, ordinary differential equation, that describes basically the dynamics of a neural network, hidden state of a neural network. Now, in terms of what kind of benefits will you get, let's look at the top one. These are reconstruction plots from data corresponding to a spiral dynamics. If you have a discretized neural network, this spiral dynamics is being able to, it's the kind of interpolation that you have is kind of edgy. But if you have a continuous time process, it actually can compute very smoothly. And also it can even generalize to the unseen area of this, which is the red part of this. And as we see here, the normal recurrent neural network misses out on this kind of a spiral dynamics. So with a continuous time process, it is believed that you can get better and better representation learning. But then the problem here is that if you actually bring these models in practice, a simple LSTM network works better than this type of network. So basically, you can actually outperform everything that we showed here with an LSTM network so far. So what's the point of basically creating such complex architectures and stuff? So this was the place where we thought that the continuous time processes that we bring from nature can actually help us build better inductive biases. So we introduced a neural network called liquid time constant networks, or in short, LTCs. LTCs are constructed by neurons and synapses. So a neuron model is a continuous process like that. It's a differential equation, it's a linear differential equation that receives the synaptic input S. It's a linear differential equation. Neurons and synapses. Now we have a synapse model. S of t is a function that has a neural network multiplied by a term called a difference of potential. That nonlinearity resembles the nonlinear behavior between the synapses in real kind of neurons. If you have synaptic connections and they are basically designed by nonlinearity, because that's actually the reality of the thing. And then if you plug in this S inside this linear equation, you will end up having a differential equation which is looking very sophisticated, but you will see the implications of this differential equation. It has a neural network as a coefficient of x of t, which is this x of t here. That neural network is input dependent. That means the inputs to the neural network defines how the behavior of this differential equation is going to be. So it sets the behavior of the differential equation in a way that when you're deploying this system on board, it can be adaptable to inputs. So this neural network, this system, if you have it in practice, it's input dependent. And as you change the input, as the result of inputs, the behavior of this differential equation changes. Now, in terms of connectivity structures, it has, if you look at the range of possible connectivity structures that you have in a standard neural network, you would have sigmoid, basically activation functions. You might have reciprocal connections between two nodes. You might have external inputs, and you might have recurrent connections for a standard neural network. Now, for a liquid neural network, instead, each node in the system is a differential equation, xj and xi. They have dynamics, and then they're connected by synapses. And then there are nonlinear processes that controls the interaction of synapses. So now, in some sense, you can think about liquid neural networks as being processes that have nonlinearity of the system on synapses instead of the neurons. So in neural networks, we have the activation functions, which are the nonlinearity of the system. Now you can think about nonlinearity of the system being on the synapses or the weights of the system. Now, in terms of practice, let's look at this application. Here, we trained an artificial neural network that can control a car, that can drive the car in this environment. And what we are showing on the sides of this middle image is the activity of two neurons that are inside a standard neural network and a liquid neural network. On the x-axis, we see the time constant or sensitivity of the behavior, of the output behavior, basically controlling the vehicle's steering angle, the sensitivity of that control on the x-axis. And on the y-axis, we see the steering angle. The color also represents the output, which is mapping between the steering angle and the outputs of the neural network, okay? So now, as we see, we added, like with liquid neural network, we have an additional degree of freedom that these networks can set its sensitivity, a liquid neural network, depending on whether we are turning, whether we are going straight. If you're going straight, the time constant, you want to be more cautious when you're taking turns, right? So your neural network, you want to be faster, so to be able to actually control during those kind of events where you're actually turning. So that's the kind of degree that you can add even at the neuronal level for interpreting these systems. Now, let's look at a case study of liquid neural networks. So usually, you saw a deep neural network for an autonomous driving application. We have a stack of convolutional neural networks. They receive camera inputs, and they can output the kind of a steering angle at its output. These kind of neural network, well, one of the things that we can do, first of all, they have like a lot of parameters in this system. What we want to do, we want to take out the fully connected layers of this neural network and replace it with recurrent neural network processes. One of those recurrent processes that we replace it with, it's a liquid neural network and the LSTMs and the normal continuous time neural networks. Now, if I replace this, I would end up having like 4 different variants. These 4 variants, one of them is called an NCP, which is a neural circuit policy that has a 4-layer architecture. Each node of this system is defined by an LTC neuron, that the equations that I was showing you, and it is sparsely connected to the other parts of the network. So we have a sparse neural network architecture here. We have then one neural network that has LSTM as the control signal and receives the perception with convolutional networks. And then we have CTRNNs and we have convolutional neural networks. Now I want to show you the driving performance of these different types of networks and what kind of characteristics is added to these systems. So first, let's look at this dashboard where I'm showing you a convolutional neural network followed by fully connected layers, a normal, very standard deep learning system that receives those camera inputs and has learned to control this car. Okay, so those camera inputs comes in and the output decisions are basically driving decisions. Now on the bottom left, what we see the decision-making process of the system. The inputs, if you realize, the inputs has a little bit of noise on top of them. So I added some noise at the input so that we can see the robustness in decision-making of this process. Now as we see, actually there is the kind of decision-making, the brighter regions here is where the neural network is paying attention when it's taking a driving decision. And we see that the attention is basically scattered with a little bit of noise on top of the system. Now, if you do the same thing and add noise, we then replace that fully connected layer of neural network with 19 liquid neurons, you can actually get to a performance of lane keeping on the same environment while having the attention of the system being basically focused on the road's horizon, like the way that we actually drive, right? So, and the fact that the parameters that are needed for performing this task, basically 19 neurons with a very small convolutional neural network as perception module, that's the fascinating part that you get from that inductive bias that we put inside neural networks from brains, okay? So if you model that, so you have like a set of neurons that you can really go through their dynamics, you can analyze them, you can understand that process of that system, and you get benefits, like real-world benefits. For example, if on the x-axis I increase the noise, the amount of noise that I add at the input, and on the y-axis I compute the output crashes, number of crashes that actually happens when the network wants to drive the car outside. We see that these are the other networks, and here we see a liquid neural network, where it actually keeps the level extremely low, LTCs. If you look into the attention map of those 4 different network variants, how do they make driving decisions when they are deployed in the environment? We see that the consistency of attention is different across different networks, while where we have a liquid neural network actually maintains its focus. And that's one of the nice things about this, but then we ask why. Why is it that the liquid neural network can focus on the actual task, which is lane keeping here? This is driving, and it's just a simple driving example where you have just, like a road and you want to stay in the road, right? Then, now, as I said, the representation that learned by a liquid neural network is much more causal. So that means they can really focus and find out the essence of the task. And then if you look into the machine learning modeling, statistical modeling is like the least form of causal modeling. It's basically you just extract, these are the taxonomies of the causal models. You have on the bottom of this axis, you have the statistical models that they can learn from data, but they cannot actually establish the causal relationship between the input and outputs. The best type of models that we could have is physical models that describes the exact dynamics of a process. Then you have basically a causal model. And in the middle, you have a kind of a spectrum of different types of causal models. So one thing that we realize is basically liquid neural networks are something that is called dynamic causal models. Dynamic causal models are models that can adapt their dynamics to, so that they can extract the essence of a task and really find out the relationship of an input-output relationship of a task based on a mechanism that is ruled out by this differential equation here. So it has parameters A, B, and C that they account for internal interventions to the system. That means if I change something in the middle of the system, there are mechanisms that can control that processes. If something that comes from outside an intervention inside the process of a system, then you would actually get into, you can control those kind of processes with a dynamic causal model. Now, a little bit, I wanted to go through the causal modeling process of a neural network. Basically, a differential equation can form a causal structure. What does that mean? That means it can predict, from the current situation, we can predict the future, one step in the future of a process. That's temporal causation. And another thing is that if I change something or intervene in a system, how can I actually control that intervention? So, or can I account for that intervention that I had in the system? So this would construct these 2 points, being able to account for future evolution of a system and interventions, and being able to account for interventions in a system. So if you have these 2 models, then you have a causal structure. So for that, I'm just skipping over this part. I just want to tell you that, I wanted to show you like more about how we're driving this connection between liquid neural networks and causal models. But I shared the slides so you can see, and also Professor Roos tomorrow is going to give a lecture on the topic that hopefully she can cover these parts. And just a couple of remarks on the performance of the network and what's the implication of having a causal model. Now let's look at this environment. We trained some neural networks. These neural networks are basically learn to fly towards a target in an unstructured environment. So we collected some data, we trained neural networks instances, and then we tested this, then we take these neural networks that we train by moving towards, like, basically these are scenes that are, a drone is inside the forest, and the drone is navigating towards a target, okay? Now we collect this data from a couple of traces, okay, that we simulate. Then we take this data, we train neural networks, we bring the neural networks back on the drone, and we test them on the drone and to see whether they can learn to navigate this task without even programming what is the objective of the task. Basically, the objective of the task has to be distilled from the data itself. And as we saw here on the right, we see the decision-making process of these networks, that liquid networks learned to pay attention to the target as the target becomes visible. That means it actually figured out the most important part of this process was really focusing on the target, even if there is an unstructured kind of input data to the system. Now, if we compare the attention map of these neural circuit policies, which is the second column, compared to the other attention maps, we see that the only type of network that learned from this data to pay attention to this target is liquid neural networks. And that's the kind of implication that you have. So you learn the cause and effect of a task using a liquid neural network that has dramatically less number of parameters compared to other types of neural networks. Now, as I told you, the relation between 2 neurons can be defined by a differential equation, by a neuron equation and a synapse equation. We recently have solved this differential equation also in closed form. And then this gave rise to a new type of neural network, which is, again, a closed form continuous time neural networks. We call them CFC. These are the closed form liquid networks. They have the same behavior, but they are basically defined in closed form. Now, what does that mean? That means if I have a differential equation, you see the ODE on the top. If I simulate this ODE, okay, the closed form solution would actually give you the very same behavior of the differential equation itself, but it does not require any numerical solvers. So it does not require any kind of complex numerical solvers. So as a result, you could scale liquid neural networks much larger to much larger instances if you want to scale the networks. In terms of performance in modeling dynamics, liquid neural networks, we see here a series of different types of advanced recurrent neural networks, and we see variants of closed form liquid neural networks and LTCs themselves that are performing remarkably better than the other systems in modeling physical dynamics. And the last thing I want to show is the difference between this understanding causality and understanding the cause and effect of a task and not being able to understand that. Now here, you see a drone, which is an agent that wants to navigate towards a target. Okay, there's a target in the environment. Now, we collected traces of a drone navigating towards this target in this forest. Then, what we did, we collected this data, then we trained neural networks, and now we brought back these neural networks on the drone to see whether they learned to navigate towards that target or not. Now here, I'm showing the performance of an LSTM neural network. So as we see, the LSTM is basically completely like looking around, and it cannot really control the drone. Is actually, if you look at the attention map of the system, actually looks all around the place. It did not really realize what's the objective of the task from data, so it could not really associate anything or learn something meaningful from the data. And then here is a liquid neural network on the same task. Look at the attention map here as the drone is going towards that target. And that's the kind of flexibility that you can learn the actual cause and effect of a task from neural networks. Now, okay, so I'm going to conclude now. I showed you this plot. I showed you that there is overparameterization regime, and we have an idea about what kind of benefits you would get in that regime and what kind of intuitive theoretical understanding do we have for neural networks. And then I showed you that there are neural networks, like liquid neural networks, that have inductive biases from brains that can actually resolve a couple of problems. For example, the robustness, while being significantly smaller than overparameterized networks. So it is not that you always have to dramatically overparameterize neural networks, but you can have inductive biases to actually gain good performance. To sum up, the law of robustness is real. So that's something that came out of a theory. Is number of parameters. It's necessarily has to be large if you want to have with effective dimensionality. So one of the ideas that we have, I'll talk about effective dimensionality here. The overparameterization definitely improves generalization and robustness, but it has some socio-technical challenges. So inductive biases or architectural motive, why do we have different types of architectures and why studying the brain is actually a good thing? It's because we can actually get smarter in designing neural networks and not just blindly overparameterizing them. So we can really put incorporating some ideas to really get what's going on. And liquid neural networks, they can enable robust representation learning outside of overparameterization regime because of their causal mechanisms. They reduce networks perceived. So that's the speculation that I have. We have to actually think about the theoretical implication here. But what I think is that the reason why liquid neural networks can pass or break the universal law of robustness is because they can extract a better or more minimum kind of effective dimensionality out of data. So you have data sets. So if the effective dimensionality get reduced by a parameterized neural network, then the law of robustness still holds, okay, given the number of data. And that's the end of my presentation. I'm just putting here at the end a couple of resources. If you want to get hands-on with liquid neural networks, we have put together like really good documentations, and I think you would enjoy to play around with these systems for your own applications. Thank you for your attention.